Now that we can use stoichiometry to calculate how much product we expect to get from a reaction, we have two variations on calculations that we can do using stoichiometry. One is to use stoichiometry to calculate the theoretical yield of a reaction, and then if we do the reaction or are given the actual amount of product that we obtained in the problem, then we can figure out what percent that is of what we expected. So this is a percent yield problem. The other problem we can have is if we have two different ingredients that we can use to do a reaction, and we want to determine which of those ingredients we're going to run out of first and how much product we're going to be able to make with that limited amount of starting material. So let's try a few examples of this. This first problem is the percent yield. We are told what we actually obtained from our reaction. So let's figure out what we should have obtained. Because remember, the percent yield is the actual yield over the theoretical yield, and then that fraction expressed as a percent. So our actual yield is given to us in grams of iron. And so that's what we need to calculate the theoretical yield, in grams of iron, not in moles of iron, not in moles of carbon dioxide or grams of carbon dioxide. We need to make sure the units match so that it's relevant. So I put some molar masses up here and another one that we're going to need for the next problem. First, we need the molar mass of carbon monoxide. So we can convert this to moles of carbon monoxide. Then we want to get iron, so we'll use the molar ratio of carbon monoxide to iron. And we have a 2 to 3 ratio. 3 moles of carbon monoxide produces 2 moles of iron. And then the molar mass of iron is 55.85 grams per mole. And so we're expecting 110 grams of iron. So that is our theoretical yield. We can put that in the denominator. You can keep a couple extra digits if you want. And now we can finish calculating our percent yield. And this gives us 72.1% of what was expected. So if we expected 110 grams of iron and we only got 79.6, that represents 72.1% of what we expected. This next problem we can tell is a limiting reactant problem because we are given both of our starting materials and we want to know how much product we can make. So we need to do a gram to gram conversion twice, once with the carbon monoxide and once with the iron 3 oxide. So here are our two amounts of starting material, 12.7 grams of carbon monoxide. We're going to convert that into the grams of iron that we can make. And then the 23.2 grams of iron 3 oxide, we're going to convert that into the amount of iron that that can make. This first one is very similar to what we just did above. We went from grams of carbon monoxide to grams of iron. And we end up with 16.9 grams of iron that we can make from the amount of carbon monoxide we have. And when we convert this to grams of iron, we get 16.2 grams of iron. So what this is telling us is that we have enough carbon monoxide to make 16.9 grams of product, and we have enough iron 3 oxide to make 16.2 grams of product. Once we get to 16.2 grams of product, we're going to run out of our iron 3 oxide. We'll still have a little carbon monoxide left, but that's not going to do anything if we're out of the iron 3 oxide. So once we get to 16.2 grams of iron, we're going to be done with our supplies, and that's how much we can actually make. So this is the answer. The smaller number is the answer because we're being limited by the amount of iron 3 oxide. Just like if you had ingredients to make a sandwich and you had a certain kind of sandwich you wanted to make, and you had enough of one ingredient to make 13 sandwiches, but you had enough of the other ingredient to only make 8 sandwiches, you're only going to make 8 sandwiches. You choose the smaller number. You don't add these or multiply these or subtract these or anything else. You just choose the smaller number. So let's just use this other reaction and try Each of these, again, a percent yield problem and a limiting reactant problem, because we have both of the starting materials here, so we know it's a limiting reactant problem. So for our percent yield, we want the actual yield over the theoretical yield, and then as a percent. And what we have obtained is 15.7 grams of our aluminum oxide product. So we want to calculate the theoretical yield in that same unit, grams of aluminum oxide. So to calculate our theoretical yield, we are figuring out how many grams of aluminum oxide can be produced from the 12.4 grams of aluminum that we reacted. How much should have been produced? So we need the molar mass of aluminum and the molar ratio, that 4 moles of aluminum make 2 moles of aluminum oxide. What we expect is that we can get 23.4 grams of aluminum oxide, and then you can either round that or keep a couple of extra digits. And it's a little crowded, but we'll put that as our denominator in our percent yield calculation. And we get 67.0% yield. If you leave off this 3 and just use 23.4 in the denominator, it actually comes out to be 67.1%. So either one of these is fine. This last digit is uncertain. So for this limiting reactant problem, we'll go ahead and do a conversion with each of the starting materials, converting grams of aluminum to grams of product, and then converting grams of oxygen to grams of product. This first one is very similar to what we just did, converting grams of aluminum to grams of aluminum oxide. This time we get 9.30 grams of aluminum oxide as our result. Then for the oxygen, we use the molar mass of oxygen and the molar ratio of oxygen. 3 moles of oxygen producing 2 moles of aluminum oxide, and then the molar mass of aluminum oxide to get 11.6 grams of product that can be produced with the amount of oxygen that we have. Again, once we get to this smaller amount, the 9.30 grams of aluminum oxide, we're going to run out of aluminum, and the additional oxygen is not going to be able to react. So this is the amount that we are actually going to be able to make. So the answer is that we can make 9.30 grams of aluminum oxide before we run out of aluminum, which is known as our limiting reactant.